Yeah, hello everyone. Today we are beginning a new series in physics. So specifically, we'll be looking at hydrostatics. The first part is all about fluids at rest, pressure, and the mystery of why things float. So let's go into our introduction slide. So, what exactly is hydrostatics? It is the branch of physics where we study fluids that are not moving. So remember that in physics, the word fluids includes both liquid like water and gases like the air around us. Unlike a solid block of wood, a fluid cannot hold its shape if you try to push it. So fluids, they cannot hold their shapes if you try to push it sideways. So it flows, water flows, gas flows. They are called fluids because they don't retain their shapes. So because of this, fluids exert pressure on a special way, or in a special way rather. They exert pressure in a special way on anything inside them. We need to understand this in order for us to build massive dams. Also, this is the knowledge that is necessary for the design of submarines and even helping us to understand how our own blood pressure works. So now let's go into some deeper concepts called density and fluid pressure. So before we go deep or go deeper, let's first talk about density. Density is simply how we or how much stuff or mass is packed into a certain amount of space. So let's assume we were trying to use a ball and we try to put a ball into a bucket. So different balls have different sizes. So assuming we had a specific size and that particular size of ball can contain a bucket, maybe a bucket or a one let me say 100-liter bucket, and we can put in like 50 balls for it to get full. We can say that the density is 50 per 1 liter. So assuming the balls were smaller, maybe 100 could enter, the density also is increasing. So this is how density works. It's simply how much stuff or mass of a particular substance can be packed into a certain amount of space. In a stationary liquid, density tells us how the pressure changes as you go deeper. Pressure is just the force pushing down on a certain area. Normally, it's always the force per unit area, it's just the force acting downwards on a particular area. However, in a fluid, this pressure pushes equally in every single direction at any point. So as you swim or you go deeper in the river, the pressure increases because you have a heavier volume of water pressing down on you from above. So imagine that you are in probably, let's say this is a pool. Let's say this is a pool. When you are at the top, just a little amount of water is above you. But as you go down, the amount of water above you is more. As you go further down, the amount of water above you becomes even more. And because of the increase in number of water above you, the fluid pressure will be more on you when you are deeper. So I hope this is driving something home. So as you swim deeper into a river, the pressure increases because you have a heavier quantity of water pressing down on you from above. So this is why deep sea submarine must be built with very strong material so that they don't get crushed by the weight of the ocean. So just imagine a river. When you go just in a river down, the pressure becomes more. Imagine when you now go into the sea, which is over 460 meters down the earth, even more. Imagine how heavy the mass of water above you would be at that point. At that point. So let's see. Let's go to our next slide, which is talking about the Archimedes principle. So to look at this, we would have to look at a very famous principle known as the Archimedes principle. It says that if you dip an object into water, the water pushes it back up with a force called buoyance or upthrust. So this is what the Archimedes principle tries to say. So how strong is the push? Is exactly equal to the weight of the water that the object pushed out of its way. So if you put a particular, let's assume we had a cup of water, we look at where the water stopped, and you dropped maybe a stone into the water, you notice that the volume of that water rise up. So that amount of rise or that raise in volume that we notice is equal to the weight of the of the water that the object was able to displace. So this is why you feel much lighter when you are inside a swimming pool than when you are standing on dry ground, because your weight, somehow the water would push you, the water would push a particular amount of your weight away. Your weight will be resting on the water. That's just how it is. So scientists use this to calculate exactly how much cargo, or how much load a big ship can carry before it starts sinking too deep. So that's the principle. The Archimedes principle is used for the laws of flotation. So depending on how large the object is, it will tell how large the amount of water the object can be able to displace away before it sinks. So another principle is the principle of flotation, which kind of works hand in hand with the Archimedes principle. So why does heavy steel like ship? Because I know, as I mentioned, ship floating. Why is it that somebody that is probably more of a visual person would be like, why steel is supposed not to float? So why does a heavy steel or a heavy ship float while small ions like nails they sink? Why does that happen? So this particular stuff is explained by the principle of flotation. For something to float, it must be able to push aside a weight of fluid that is equal to its own weight. So a big ship is mostly hollow and full of air, so its average density is much less than the water. So this is clever. This is like the clever design that allows the water to generate enough upthrust to carry the whole ship, because of the fact that the ship is hollow and can carry some amount of air. Air does not stay inside water, it always wants to float. So because of this reason, it uses the principle of flotation, allowing the ship to be able to displace an amount of water that would be reasonable enough for the ship to float. So now, that being said, let's see some of the mathematics that's involved in this hydrostatics. Yeah, so the hydrostatics formula, in order for you to be a very good physicist or a very good physics student, we need to put these ideas into maths. So, and to do that, we would use a formula to find the pressure at any depth. So the formula for that is given as this: P equals P naught plus rho GH. I said rho because it's looking like P, but that P is not really P, that's density. That's this one here. This P, this looks like P, is not P, it's density. So the formula here, P naught is the air pressure pushing on the surface, while P is the normal pressure, that is the pressure that the object is exerting. So the other part, like P, this portion here, pH or pGH, is what we call the gauge pressure. The gauge pressure. So this is like the extra pressure caused just by the liquid itself. It depends on the depth. It depends on, that's the depth H. It depends on the depth H. It depends on the density rho, that's this here. And it depends on the gravity, that's acceleration due to gravity, G. So this formula helps us to account for all the layers of the liquid pressing down on a particular object. So let's see some real-world applications of these hydrostatic laws. So these laws are used in everyday studies or in everyday things that we see. We might not really know that they are being applied, but they are. So think of the hydraulic jacks used in mechanics, or used by mechanics rather, to lift cars. All those kind of stuff that you see that they use when maybe they want to change tire. They use fluids to multiply force. It uses the principle of hydrostatics. So the same thing happens in submarines, which use ballast tanks. And these tanks are being filled with water to sink and blow in the air to rise back up. So how submarines are able to go deep underwater and stay deep is because they are filled with water. But now there's also another dynamics that allows them to also rise back up by releasing off air. So they have tanks that are filled with water and another tank that's filled with air. So when it wants to rise up, it offloads, it gives off the air and it comes up. But when it wants to go down, it takes in the water and sinks down. So even in dams, we use you use this principle of hydrostatics for electricity. So we use these same principles in dam to generate electricity. So even in dam we use for electricity. In the dams we use for electricity, sorry, they are built much thicker at the bottom than at the top, so as to handle massive pressure that happens at the base. We said that as you go down in a deep water, the pressure down is larger. So that's how they construct dams. They make them look something like this, something like a triangular base. So their base is always thicker. It's always thicker, so as to allow them not to collapse. Because just imagine the pressure from water flowing, maybe flowing towards the dam. If the base of the dam is not constructed to be wide or strong enough, it would collapse the entire dam wall, because the dam is usually a big, huge wall. So water has strong pressure, and this pressure is called the hydrostatic pressure. So now, in conclusion, we have seen that density and depth are the main reasons why pressures exist in fluid, and we also learned that pressure acts in all directions to liquid in fluids rather. And also we looked at how Archimedes' principle and flotation allows us to understand ships and how heavy machinery floats. So these laws are bedrock of modern engineering and naval science. So see you guys in my next lesson.